Hello, welcome to Introduction to Computational Fluid Dynamics Part 2. I'm Hugo Castillo Sanchez, and in this video I would like to show the research I have been doing over the last years related to CFD. I'm mostly interested in the simulation of complex fluids. That means fluids that do not behave like a standard, such as air and water. Standard fluids are water and fluids, but I'm interested in for instance, the behavior of polymers, the behavior of plastics, the cements, muds. So, yeah, in this video, I will also like to show some simulations I have carried out using computational fluid dynamics software. So, yeah, I will show these results at the end of the presentation. But first, I would like to give a brief introduction to what is a generalized Newtonian fluid. So here I'm reporting two curves. So the first one shows the behavior for different fluids of the shear stress versus shear rates. But what are exactly these physical quantities? So in order to explain those quantities, I also need to explain the types of deformations that are observed in fluids like in fluids or in elastic materials or in bodies. So here I'm using a Cartesian coordinate system, so we have x, y, and z. So first I will focus on explaining what is an extensional deformation. So we have a cube of a fluid. It can also be an elastic material. So I'm going to apply a force over this surface. So this force will stretch the fluid in x direction. I might also apply a force on the opposite surface, also in the opposite direction. So I'm causing an stretching of the volume control. So the new configuration of the material is going to be this one. So extensional deformations are known as volumetric deformations, where the volume of the fluid is going to change. However, the shape of the material is going to remain the same. So how do we measure these deformations? So we calculate the derivative of the velocity in x direction with respect x, because the fluid or the material is moving in this direction, and also the changes are happening in x direction because we are applying a force in this direction in x. Nothing is really happening in y. So if you remember your physics lectures, the velocity can be expressed as the derivative of the length with respect time, or the derivative of the position with respect time. So this derivative can be expressed as this one, but we also can make some modifications to this derivative. So we use the chain rule. So we switch derivatives and we obtain the following quantity. So this derivative of the length is this one. How does the length of the material changes with respect to the position x? So this quantity is known as a strain, which is defined in a few words as the relative deformation compared to a reference position configuration. So we are comparing this new length with respect to the original length of the volume control. So this derivative also tells us how does the configuration of the material, how does the configuration of the material element changes in the same direction. This stretching we are imposing, causes expansions or compressions. In this case, we are stretching the polymer over here. So we are causing an expansion of the material. What we might also apply a force in the opposite direction here, and then we will now compress the material. So this is the basic definition of extensional deformations. But also, if this derivative is zero, that means that we are not stretching the fluid in x direction, or the stretching is very small. So that means that the new configuration is not going to vary with respect to the original position. So for fluids, we are mostly interested in the rate of change of the strain. So we have the strain rate. And on the other hand, we have the shear deformations. So here, instead of applying a force over this surface, we will apply it over this surface. So we will apply a force in this direction, which will cause the following deformation. So we observe that the shape of the volume control is going to be different, but the volume is going to be the same with respect to this volume control. So yeah, shear deformations are also known as tangential deformations. So in this kind of deformations, there is an angle. An angle is going to be formed here, which is going to be different to the one observed here. So the length of the volume control is going to vary in y direction, but the deformation, the direction of the force is going to be applied in x direction. So how do we measure the shear deformations? So we use, instead of this derivative, we use this one. So we measure how does the velocity in y direction changes with respect to x position, x direction. So doing something similar compared to this case. So we express the derivative of we express the velocity in y direction as the derivative of the length in y direction with respect to time, but we switch derivatives using the chain rule, and we obtain the following quantity. So here, this derivative is known as it's also the strain rate. The derivative with respect time of this quantity is known as the strain rate, which is in a few words defined as the relative displacements between parallel planes of a material. So yeah, so basically this quantity is telling us how the angle of this deformation varies with respect to this original position. And the force that we are applying over here is known as shear stress, which is the force applied over a fluid to deform the material. So here we have, for the extensional deformations, we have an extensional force, but here we have a shear force or a shear stress, because stress is defined as the force applied over a surface, over an area of a fluid material. In this case, in extensional deformation, we were applying a force over this surface, so we have the extensional stress. But here in this case, the tangential force is being applied over this surface, so we have the shear stress. So we have the shear deformation where there is a variation of the shape, but the volume of the volume is going to be the same compared to this case. So now that we have explained these concepts, for fluids, simple fluids, so yeah, we have the shear stress, which is the force applied over a surface material to deform a fluid, and the shear rate, which is this deformation, this quantity. So for simple materials such as water, we will observe a linear behavior of the shear stress versus shear rate, and this behavior is known as Newton's law of viscosity. So very simple fluids such as water will exhibit this linear behavior, and the slope of this curve is known as the viscosity. The higher the slope, the higher the value of viscosity. And viscosity, in a few words, is also known as the resistance of a fluid to a change in shape or movement at a given rate, or using even simple words, the viscosity can be seen as a measure of a fluid's resistance to flow. So for Newtonian fluids, the viscosity is always going to be constant if we plot it against the shear rate, against this derivative. But yeah, those fluids are very simple, but in the industry or in our daily life, we encounter more complex fluids. That means fluids that do not behave like Newtonian fluids, like fluids that exhibit a linear behavior between the shear stress and shear rate. We might have fluids that behave as shear-thinning, or fluids that behave as shear-thickening, where we observe a non-linear behavior. Shear-thinning is a phenomenon that some fluids exhibit, where the viscosity of the fluid is going to decrease as the higher the deformation we are applying to the fluid. Some very basic example of a shear-thinning fluid is, for instance, chocolate, or also you have probably encountered this kind of fluids when you are painting, for instance, the wall of your house. So you will use a brush, you will use some paint, and then you will apply this paint into your wall. And you will notice that at first, when you are starting to paint your wall, you will notice that the viscosity of the paint feels viscous. But the longer you apply the force with your hand, so you are applying a force over the brush, and with this brush you are applying the paint over the wall. So you are applying an stress, because you are applying a force over your wall, which has a surface. So the longer you apply this force with your hand and the brush, you will notice that the viscosity of the paint is going to decrease. You will notice how it is becoming easier to paint, because the viscosity of the fluid is decreasing. So that's a common example of a shear-thinning fluid. So we encounter this kind of behavior a lot in the industry. So plenty of materials exhibit this behavior. On the other hand, we have the opposite behavior, which is shear-thickening, where the viscosity, instead of decreasing, is going to increase the higher the deformation you apply, or the higher the force you apply over the material. And these kind of materials are not super common, but they happen. This behavior happens a lot in some cases. Some very basic example. The most common example is a mixture of cornstarch and water. So I will actually show an experiment where I illustrate the shear-thickening behavior at the end of this video. So please stay around if you are interested in seeing this behavior in daily life. So, but in a few words, yeah, shear-thickening, we observe an increase of the viscosity versus the shear rate, or the shear stress. The higher the force you apply to the fluid, you will observe an increase in the viscosity of the material. So how do we model these behaviors? So we use very basic power law equations. So here we have the viscosity that, as I said before, is a measure of a fluid's resistance to flow. So the viscosity is a physical property of a material. So every fluid in the world has a viscosity value. So for these materials, for these behaviors, we can model them using this equation, where we have a viscosity 0, which is usually constant. It can be the viscosity at a given temperature. And then we have the shear rate, which is this quantity that I mentioned before. And we have a superscript n minus 1. So I also forgot to mention that in simple fluids such as water, we will only observe shear deformations, and extensional deformations are not present in water. These kind of deformations are more common in, for instance, plastics or polymers, where those materials are composed of a solvent, water, and long macromolecules, and these macromolecules can behave as elastic materials, and these molecules can be stretched and can be compressed. So these kind of deformations are more common in those kind of materials like plastics. But yeah, going back to this explanation, so yeah, the viscosity can be calculated using this equation, which is known as the power law model. And then this shear stress, which is the force applied over a surface material, can be calculated as the product of the viscosity multiplied by the shear rate. As I said before, those quantities. And yeah, we substitute this equation into this one, we obtain something like this. So if the superscript is equal to 1, we have the linear behavior we observe here. So yeah, when n is equal to 1, we obtain the equation that is used to describe simple fluids like water. On the other hand, if the superscript is smaller than 1, we have the shear-thinning behavior, which is this behavior where the viscosity is going to decrease. And if the superscript is greater than 1, we will observe the opposite behavior, which is shear-thickening. You can plot, you can use this equation to plot this behavior. You can assign a constant value of n, and then you can use different values of shear rate, and then you can calculate the shear stress, and you can obtain this kind of curves, and you will see that you will obtain the same behavior that I am reporting here. So another interesting behavior that I have studied over the last years is known as viscoelasticity or viscoelastic materials, which in a few words are those materials that exhibit both viscous and elastic behavior when undergoing a deformation. So in order to explain viscoelasticity, I also need to explain Hooke's law of elasticity, which is a simple law that explains the behavior of springs. So you have a spring here represented by this figure. So this spring has an initial configuration called L0. So you will apply a force and a stress to the spring, and then you will stretch it, and then the new configuration is going to be L. So the deformation of the spring is measured with this quantity, which is the strain. So we compare the L, the new configuration, over the initial configuration, L0. So we have the strain, and then the stress can be calculated as the product of the elastic modulus, which is a physical property. It's the equivalent of viscosity for fluids. So elastic modulus is the physical property that measures the material, the spring resistance to being deformed or to being stretched in this case. And another interesting property of springs is that the springs remember always its initial configuration. We tend to say that the springs have a perfect memory because, as I said before, we were stretching a polymer in this direction, so we were applying a force, and then the spring reached a length L. But as soon as we remove this stress, the spring will return to its initial configuration. The springs always remember its initial configuration. That's why we use the concept of memory. On the other hand, we have the Newton's law of viscosity, which I already explained a few slides before. So yeah, fluids respond to forces by moving, and the stress depends on the shear rate, unlike elastic materials. For elastic materials, the springs respond to the strain, the formations, but fluids respond to the derivative of the strains. So that's why we use this gamma dot. Gamma is known as the strain, and gamma dot is the strain rate, the derivative of the strain with respect to time. So yeah, as I said before, the shear stress for a fluid is equal to the viscosity multiplied by the shear rate. Yeah, and the constant, this coefficient, is known as viscosity. And we sometimes use a dashpot to explain the concept of viscosity. We place a fluid, a viscous fluid, over the container, and then we will apply a stress or a force in this direction. So the dashpot is going to can move, but the higher the viscosity of the fluid, the more resistance the dashpot is going to face. So if the viscous fluid, if the fluid has low viscosity, this dashpot can be moved easily. But on the other hand, if the viscosity of the fluid is higher, it will be much harder to move the dashpot. So yeah, so why these concepts were useful, or how they can be useful to explain viscoelasticity? Well, the thing is that polymers, polymeric materials, and fluids composed of molecular chains are not ideal elastic materials because, as I said before, in a perfect elastic material, a perfect spring, when you stretch these springs, they will return to its initial configuration as soon as you remove the force you were applying to it. But polymeric materials do not behave like perfect springs. So when you stretch them, and as soon as you remove this force you were applying, they will never return to its initial configuration because they have a dissipative reaction to deformation. So usually polymeric materials can be seen as a spring, but connected to a dashpot. So fluids exhibit a viscous contribution, will exhibit a viscous part that will oppose to deformation. So yeah, we tend to say that fluids, polymeric materials, will not remember its shape forever. So there is a characteristic time that is representative of viscoelasticity. So this characteristic time can be calculated as the viscosity, the ratio of viscosity and elastic modulus. So here I'm illustrating one of the most common equations that is used to represent viscoelastic behavior, which is this equation, which is known as the upper convected Maxwell model. So Maxwell is the same guy that studied electromagnetism. So if you know Maxwell equations for electromagnetism, this is the same guy. This guy was studying viscoelastic materials. So he developed this equation, which is a bit complex to explain now. But here we have the stress, which is known as the stress tensor, which is a matrix, 3 by 3, 9 components of the stress tensor. And then we have this complex derivative, which measures derivatives changes with respect to time and position, and then these other elements that I'm not going to explain by now. But these kind of derivatives are used to get an accurate representation of viscoelastic behavior. And then this tensor, this matrix, is known as the deformation tensor, which is calculated as follows: the gradient of the velocity plus the transpose of the gradient of the velocity multiplied by 1/2. So this deformation tensor tells us a lot about the kind of deformations that a fluid might experience. So that's why this tensor is important to study deformations in fluids. Because if you know the velocity of a material, how a fluid is moving, or a polymeric material is moving, if you calculate this tensor, you can get all this kind of information that I showed before. And yeah, this equation looks a bit similar. For instance, we have a combination between Hooke's law and Newton's law of viscoelasticity. And how viscous or how elastic or how viscoelastic our material can be. So we use a dimensionless number known as the Weissenberg number, which is expressed as this characteristic time I was showing before, multiplied by a characteristic velocity and a characteristic length. These parameters are usually obtained from the geometry of where a fluid is flowing. It can be a channel, so this velocity can be the maximum velocity that the fluid is experiencing, and this length L can be, for instance, the height of the channel. So if you calculate this number, and if this number is 0 or tends to 0, we will observe a liquid behavior. So if we substitute this value into this equation, this derivative, this complex derivative is 0, and then you recover Newton's law of viscoelasticity. No, Newton's law of viscosity, which is the equation I show here. But this is in tensor form. On the other hand, if the Weissenberg number tends to infinity, you will mostly observe elastic behavior. So yeah, you substitute this number, this derivative is going to dominate. You can do some algebra, and then you will recover Hooke's law of elasticity. So viscoelastic behavior, that means a combination between both elastic and viscous behavior, is observed when you have middle intermediate values of Weissenberg number. So now moving on to the part of simulation results I have done in the past. So I simulate shear-thinning and viscoelastic materials in channel flows. So this is the geometry of a channel. So we have the dimensions of the channel. So the channel is 10L. So L is the channel height, which can be 1 meter. So the total length of the channel is 10 meters. So we also have the following boundary conditions. So at the walls, we have non-slip boundary conditions. That means that the velocity at these walls, at this one, and at this one, the velocity is going to be 0 there. So that means that the fluids that are very close to the wall will almost not move. And then in computational fluid dynamics, we tend to impose a velocity. In this case, we impose a parabolic shape, which will adopt this form. So in CFD, we impose this velocity here at the inlet, and then we solve the equations with time and with position. And then at the outlet, we set fully developed boundary conditions. That means that the quantity such as velocity is not going to change at this point. So yeah, so we simulate a fluid that exhibits shear-thinning behavior. That means that we will observe a decrease of the viscosity when the shear rate or the shear stress is being increased. So if you remember the slides that I show in the part 1, in the video previous to this one, we carry out a meshing. So we specified the geometry, and then we split this domain into smaller cells, and we use hierarchical grids. So we were interested in the behavior very close to the walls. So that's why the cells close to the wall are smaller compared to the center, because the center, we are not really interested what is happening there, because it's behavior very predictable to observe. So we use an uniform Cartesian mesh with these cell sizes. So the size of the cell in x direction and the size of the cells in y direction is going to be the same. And we use a time step, the 1 multiplied by 10 to the minus 4. And then, yeah, we use 2 meshes to simulate the flow of a shear-thinning behavior of a shear-thinning viscoelastic fluid. And yeah, we solve the governing equations until we reach time equal to 8. For a more detailed information about these simulations, you can see my papers that were published in 2023 and 2024. And if you are interested in seeing my work, and you can request a copy, and I will provide it for free. So you can be in touch with me, and I will do that for you. I will send you a copy. And then, yeah, we solve the governing equations, and then we obtain the following profiles. So those are steady state profiles. So that means when the these quantities are not going to change with time. So we report these profiles at this position. So we have velocity profile and viscosity. So for instance, the velocity, we observe a parabolic profile. So this is the channel coordinate. So that means this coordinate y, and we are observing how the velocity is going to vary along the channel height. So as I said before, this profile shows respects the boundary conditions. So the velocities at the walls are going to be 0, but we observe a maximum velocity at the center. So we were expecting this behavior because it's common in any kind of fluid that in channels we observe a maximum velocity at the center. But we were mostly interested at what was happening at the wall because the viscosity was going to vary there. So this is a shear-thinning behavior. So because the viscosity is going to decrease as we get closer to the wall. And this is because the shear rate of the changes of the velocity very close to the wall are increasing. So the derivatives of the velocity here are going to be greater. So that's why we are observing a decrease in viscosity close to the walls, because the shear rates are higher here. And we also have these two profiles, which are standard profiles. This quantity is known as the normal stress, which is the shear force that is being applied in x direction over the surface where the normal points in x direction. So this normal stress measures extensional deformations. So as I said before, these quantities are only relevant when we have materials that exhibit viscoelastic behavior, or materials that have, for instance, a combination between a solvent, water, and a polymeric material that, as I explained before, polymeric materials can behave as springs, non-ideal springs. So for fluids like water, this quantity is going to be 0, but in this fluid that I was studying, this fluid was showing viscoelastic behavior. There was some level of elasticity in our fluid, so that's why we observe that this quantity is different than 0. So yeah, this quantity tells us at some degree the level of elasticity of our fluid. The higher this quantity is, the higher the extensional deformation. And yeah, I also forgot to mention that I was carrying out simulations of these flows in 2 different CFD software. Rotool, which is a toolbox based on OpenFOAM. So I was using a CFD software that uses the finite-volume-method, and then HighGFlow. The results that I obtained in HighGFlow are in red. So HighGFlow, if you remember, is a CFD software I was working with that uses finite-difference-method. So I was comparing the 2 simulations from 2 different software that use 2 different numerical methods, and I was obtaining the same results, which was part of my job when I was doing my postdoctoral research in Brazil. So I also carried out simulations in a more complex geometry, which is known as the planar for-one contraction flow, which is a geometry that can be used in the industry. So for instance, in extrusion operations where you have a long channel, a very big channel with length equal to 4L. So yeah, this geometry is known as 4-1 because the big channel is 4 times bigger than the smaller channel. So yeah, we will make a fluid flow over this long channel, this big channel, and then we will compress it. We will make it flow through a smaller channel. So some characteristics of the geometry of this channel are, for instance, the bigger channel has a length of 20 meters, and the smaller channel has a length of 25 meters. Yeah, so in order to simulate this kind of geometries, in CFD we also impose a parabolic profile that adopts this form, and then yeah, which is this one adopts this form where the u0 is the central line velocity of this channel. Also, we impose boundary conditions here. We impose non-slip boundary conditions at these walls here and here, but also here and here. So that means that the velocity of the fluid close to these walls is going to be 0. And in CFD, as I said before, we impose a velocity here. So we will solve the governing equations. That means the continuity, the momentum, and the constitutive equations, which are the equations that I show here and here. So we solve those equations with respect time and position. So how the velocity is going to vary here in this direction, and also with respect time. And then, yeah, here is the cells, the mesh we use to simulate this flow. So we have bigger cells very far from the contraction region. We also have intermediate value cells here, but as much smaller cells close to the contraction region, because we need that our solution, our numerical solution is, we need our numerical solution to be as accurate as possible here in the contraction region, because the most interesting behavior is going to happen here. And this is because in this kind of geometries we observe some formation of vortices at the corners. So we wanted to see if our simulations are able to reproduce those vortices at the corners. So this is a figure that I obtained in high-G-flow software, where we are reporting two different things. So we are reporting the velocity magnitude of the fluid here. So as you can see, the values in red are telling us that we are observing higher values of velocity at the center of the smaller channel, and the values of the velocity close to the walls are almost 0, and this is because we were imposing non-slip boundary conditions there. You can also see here that the velocity is 0 here at the corners of the small channel, and then intermediate values of velocity here near the contraction. And then these white lines are known as streamlines, which are lines that are tangential to the instantaneous velocity direction, which means, for instance, if these streamlines are horizontal, that means that the velocity is mostly relevant in x direction. So there is mostly movement of the fluid elements in this direction. But here we have both contributions from the velocity in x direction, because the fluid is moving in this direction, but also is moving in y direction. So we have also a contribution from the velocity vector in y direction. And then, yeah, and a streamline can also be seen as paths that are traced out by fluid elements as they move with the flow. So streamlines are used by engineers to study how the fluid elements are moving through the geometry. And these streamlines allow us to calculate or to obtain these vortices at the corners. So our simulations are able to reproduce these vortices at the corners. And part of my research was also to compare two CFD simulations. As I said before, HighGFlow is the software, the CFD software I was working with that uses finite-difference-method to solve the governing equations, and Rotool, which is based on OpenFOAM that uses finite-volume-method, and then we compare the two streamlines from both CFD software, and you can see that they predict roughly the same behavior. The size of the vortex from obtaining HighGFlow is basically the same as the one obtained in Rotool. And yeah, just these results can be found in my research papers that were published in 2023 and 2024. And then, yeah, my most recent research was studying the behavior of suspensions of spherical particles. So my colleagues in the United Kingdom developed a model for dense suspensions of perfectly smooth spheres. So I'm not showing actually the full model because it is mathematically speaking is a really complex model. So there is no point in showing here the model. But if you are interested in seeing the model, you can check out their paper. So their model consider two particles that were interacting with each other. So their model were ignoring intermolecular forces such as van der Waals forces and frictional forces. So they only consider hydrodynamic interactions. That means that the particles, there was a solvent. There is a solvent in the suspension. So there is going to be some fluid between the two particles. So yeah, we were only considering, the model only considers lubrication forces, which is the forces that originates when we have a solvent over or between two particles interacting with each other. And the particles do not touch each other, so finite gaps remains between them. And their model express the stress tensor, which is a matrix of 3 by 3 elements, is expressed in terms of the orientation unit vector. That means that the vector that separates this vector that is illustrated here. And their model was useful because they reproduce some interesting behavior for suspensions, which is the shear-thickening behavior that I show here. So simple shear flow. Before showing the behavior of suspensions, the shear-thickening behavior of suspensions, I need to explain what is a simple shear flow geometry. This geometry is one of the simplest geometries that can be simulated in CFD. So we have two parallel plates, and a suspension is placed between these two plates. And then the velocity at the bottom plate is 0. That means that it's going to be fixed. And the fluid that is very close to the wall is not going to move, or is going to move with a very, very slow velocity. On the other hand, the top plate is moving with a velocity u0. The velocity here is going to be equal to u0. And we can define the shear rate, which is calculated as the derivative of the velocity with respect to y, and can be calculated as follows. It's just the ratio of u0 over L, and this shear rate is always constant. So these kind of geometries are used to estimate the viscosity of a fluid, because there are special machines called rheometers where you have two plates separated by a distance L, and then you place a sample of fluid here, and then the machine will apply a force at the top plate, and then will make the top plate move with a velocity u0. So from the machine, you know the shear stress because it's the force that the machine is going to apply over this surface. And then you also know this quantity, the shear rate, which is calculated as follows. You already know the distance between the two plates, and you of course know the velocity at which the top plate is moving. So you remember the Newton's law of viscosity, which is this one. The viscosity can be calculated as the ratio between the shear stress and the shear rate. And this kind of geometries are used to estimate the viscosity. And then for a suspension, we observe this kind of behaviors where we report the viscosity versus shear rate. So where the viscosity is very small at when the velocity values are 0. But when you deform the material, when you increase, let's say, the velocity, you will observe a rapid increase of viscosity, or the viscosity of the suspension. And this increase in viscosity is actually happening very quickly because here, for instance, in this interval is really small, but you observe really rapid increase of viscosity that goes from, for instance, this is a logarithmic scale, so you can see how, for instance, the viscosity goes from 50 to, let's say, 800 in just this small interval of shear rate. So, as I said before, this is shear-thickening behavior. And here I was comparing the results that were published by my colleagues that are in red with the results I obtained in high-G flow. So each point here represents a different simulation. So for instance, these points were obtained when the velocity was 0.0001. These values were obtained when the velocity was 0.001, and so on. So yeah, the points were obtained for different values of velocity. And now I would like to illustrate this behavior using an experiment that I did at my home. I mix cornstarch with water, and then I will show it to you in a second. Now I would like to show this experiment I made at home, which consists of mixing cornstarch with water. So you can do it also by yourself at home. It's really easy to prepare. This fluid is known as Ooblek. So here you can see very quickly that I have this paste, this Ooblek, and then I'm using a spoon to apply a shear force over this fluid. So I'm basically moving with my hand. I'm deforming the fluid, and then here I want you to see that I'm applying very small, very weak force, and then you can notice that the fluid is moving easily. So that's not a surprise, but the higher the force I am applying with my hand, you can notice that it's getting really hard to make the fluid move. You can even see that the recipient is moving because the fluid is getting super viscous, hard to move. So the resistance of the fluid to move, to flow, is increasing the higher the force I'm applying with the spoon. So again, I am applying a high shear rate, a high shear force, and the viscosity is increasing quickly. And then I'm also going to use this hammer, wood hammer, and yeah, I'm applying a very weak force to it, and yeah, the viscosity of the fluid is low, so there is no problem making the fluid flow. But now I'm going to apply a much higher force, and I want you to see the behavior. You can see that the fluid is increasing, the viscosity of the fluid is increasing, and the material is behaving like a solid. You can even hear the sound I'm going to repeat it again. You can hear it by yourself in a while. So I'm going to apply a low force there, low shear force. But then, yeah, you can see the shear thickening behavior, that at low shear rates, at low shear forces, the viscosity of the fluid is low, but the higher the force, the higher the viscosity of the fluid. So just hold on a second, and you can hear how the viscosity is much higher. There is a high resistance of the fluid to flow. So this behavior is known as shear thickening. So this particular behavior is seen in suspensions. So this behavior is also being used to design vests, that bulletproof vests for security. Shear thickening behavior is also being used to design cell phone screen protectors. So some researchers from the UK have designed, for instance, they place a fluid, a shear thickening fluid, in a screen protector. So, for instance, if your cell phone falls from your pocket or falls accidentally, it will hit the floor with high impact. So, yeah, it will impact the floor with a high force. So, the fluid that is between the screen protector and the cell phone will react to it by increasing its viscosity. And this behavior that we are observing here will act like a protector, so the main screen of your cell phone will not break. So yeah, this is those are some applications of shear thickening behavior. What we observed in the experiment is that at low shear rates we were here, at low shear forces we were in this region, but as soon as we applied a higher force, a higher value of the force with the spoon, we observe a quick increase in the viscosity, and the fluid was almost behaving as a solid. So I just wanted to conclude with that experiment. So thank you everyone for being here. If you made it this far, I appreciate taking the time to watch my videos. So I have also included some references in case you are interested in checking them out for more details and for more detailed information. For instance, here is the paper that reports the numerical method used by HiGFlow, the software, the CFD software I was working with in Brazil. This is the Rotool CFD software that was specifically designed to simulate complex fluids. So you can download it from this website. And yeah, here I report some the papers I published in 2021, which shows the simulations I reported here in this presentation. And then, yeah, the models, in case you are interested in the models for suspensions that I was talking about here, where they report this behavior of suspensions, you can check these papers out. And yeah, these are my papers. So in case you are interested in a copy, I can provide them. I can provide a copy for free. So let me know. And thank you once again. See you in the next video. What we observed in the experiment is that at low shear rates we were here, at low shear forces we were in this region, but as soon as we applied a higher force, a higher value of the force with the spoon, we observe a quick increase in the viscosity, and the fluid was almost behaving as a solid. So I just wanted to conclude with that experiment. So thank you everyone for being here. If you made it this far, I appreciate taking the time to watch my videos. So I have also included some references in case you are interested in checking them out for more details and for more detailed information. For instance, here is the paper that reports the numerical method used by HiGFlow, the software, the CFD software I was working with in Brazil. This is the Rotool CFD software that was specifically designed to simulate complex fluids, so you can download it from this website. And yeah, here are reports on the papers I published in 2021, which shows the simulations I reported here in this presentation. And then, yeah, the models, in case you are interested in the models for suspensions that I was talking about here, where they report this behavior of suspensions, you can check these papers out. And yeah, these are my papers. So in case you are interested in a copy, I can provide them. I can provide a copy for free. So let me know. And thank you once again. See you in the next video.